Today we are going to talk about balanced torque. But before we started with the balanced torque, let's remember what is the torque. Torque, before that, we need that torque is a force that's to make an object turn or rotate. So if you have an object, any object, you need to rotate it or to turn it around, apply a torque. Torque is produced by turning force and tends to produce rational acceleration. Now, and force and torque are different. If you need to translate an object from point to point in a linear or in a line, you apply a force. But if you need to apply or to move object from angle to angle, you apply a torque. So the torque and the force are different. Force makes the object accelerate, and the torque makes the object rotate. Now, and the torque, the formula for the torque was force times the lever arm, where the lever arm means the distance from the turning axis to the point of contact, as we said in the last lesson. So torque is a force times the lever arm or force distance times sine of the angle between them, where the lever arm here or the distance here is a distance from the turning axis up to the or until to the pivot point. This is here the meaning of torque. Today now we are going to talk about balanced torque. Balanced torque looks like net force is zero or balanced force. As we have balanced force, we have balanced torques. When we say like the balanced torques, like if we the balanced force, sorry, like as an example, if we have object, you apply here 2 Newton to the right and 2 Newton to the left. So when you find the net force, after the right minus after the left equals 0. So here the object will stay at rest. The object will not move. So we say that these are balanced force. And as we have balanced force, we have balanced torque. Balanced torque, that means there's no change or rotation. I have this object here. I rotate it to the clockwise with some amount of Newton per meter, and there's another object that rotates. I rotate the object counterclockwise with the same amount of Newton per meter. So here we have the same amount of torque in different direction. So I have balanced torque. I have the torque here R0. There's no change in rotation. As an example, children of unequal weight can balance on a seesaw by sitting on a different distance from the pivot point. Now, you have here 2 children. One is sitting here and the other one is sitting here. The first one here, his weight is 2 Newton, or you can say 12 as an example, and so on. And the other one here is 36 Newton. And all of us know that the heavy object will lay down and the light one will go up. They are different in weight, but we can make them sitting in balance. How? By sitting in the different distance from the pivot point. Here, both of them are sitting like this here. Both of them now are sitting at an equal distance. This is the first one. He's sitting at distance 3 meters. And the second one here, that's sitting with 3 meters, as an example now. The first one here, his weight is 36 Newton. And the second one here, his weight is 12 Newton. So I know that there's no one, his weight 36, but this is an example. Now, Here now, as you see, they are unbalanced. I want to make them balanced. To make them balanced, I want to change the distance from the first one to the pivot point and the second one to the second. I want to change the distance of the two children sitting from the pivot point. Such as, let's make them the first one. Just a second, please. 72 over 12. How? I can imagine that this is 12, this is 36, and if this is x, this will be 6 minus x. And this is not with you, but this is a way to meet in order to find where should the first boy sit in order to get balanced with the second boy. So after I say now, since they are balanced, so 12x equals 36 times 6 minus x. So then x will be 4.5. So that's mean the first boy, when he's sitting at a distance 4.5 meter from the pivot point, he have the same torque as the second boy sitting at a distance of 1.5 meter. So now, after that, when the first one sitting here, and the second one get far away with 4.5 meter from the pivot point, both of them now have the same torque. So here, now let's come back to our lesson. So that's mean here, I can make them have the same torques by changing the distance from the pivot point. The first one here, as I told you, they are sitting 3 to the pivot, and the second point, they are 3 from the pivot point. How can I make them balanced? By change the distance from the pivot point. I let the light one sitting 4.5 meter from the pivot point, and the heavier one sitting 1.5 meter from the pivot point. In order now, let's see that how they are balanced. The first case here, when they are sitting 3 by 3, how can we find the torque? Torque is force times distance. So the torque for the first boy is 12 times 3, which is 36 Newton per meter. And for the second one, the torque here was 3 times 36, force times distance. 3 times 36, it was 108. So now, as you see, they are unbalanced. Torque. Because the torque for the second boy is greater than the torque for the first boy, so it makes them unbalanced torque. As we have in the boxes, 12 Newton to the right and 10 Newton to the left. So that's mean it's let the box go to the right. Here, it's let the seesaw go down to the, oh, it's mean like it's go clockwise to the second torque. Now let's see that the second case here. The second case, 12 times 4.5, which is F times D, which is torque 1. Does it equal the second torque here, 1.5 times 36? Let's see. If you multiply 12 times 4, 48, 12 times 5.56, 48 plus 6 plus 54. So 54. And then 1 times 36.5 times 18, 18 plus 36 will be 54. So they are the same. Since they are the same, so I will say that this is our balanced torque. This is now the difference between the balanced and the unbalanced torque. Is it clear?
Yes. Teacher, since we increased the distance of 4.5, why we didn't increase it in the other one? Like why we didn't make it as, for example, 6.5?
No, I not increase it. I increase one and I decrease the other one. And I let them, both of them, change the same, change the distance. You are in the same season, so you cannot say one sitting at 8 and one. The distance between them must be 6.
Like teacher, you mean like this whole distance, it's equal 6. But when you increase this up, it will be 4.5, and the one that you decrease it down,
Yes.
it will be 1.5.
This boy here, he's changed his place to sitting here. And the other one, he's changed his place to sitting here, in order to have the same distance between them. Or you can say, like, if you have them, or if you have a pivot point, you have changed the distance of the pivot point. Let's the pivot point here. So 1.5 from the pivot point, you have a heavier boy, and 4.5 from the pivot point, you have a light boy.
Okay, teacher. Thank you.
Yeah. Let's come back now. And there's a scale balance. Scale balance with sliding weights are based on the balance torques. As later on we will see an example. Let's see what is the scale balance. Like then you go to the hospital and sometimes measure your weight. If there's sometimes you have a scale balance. This scale balance, they use the same as the balance. This is to change the position of the balance in order to find your weight. After that, I will give you an example. Now, let's come back here. So a very basic concept when dealing with torque is the idea of balance. In general, if the object acted on several torques at the same time, this is here, they are, as I repeat them, that the torque is a vector quantity. That means when the vector is, since it's a vector, so that means you have direction and magnitude. Now, if you have the same direction, if they have the same direction for the torques, that means you have to change the amount of torques in order to make them balance, or you can change the direction in order to make them balance. So to make them have equilibrium or balance or have the net zero, the net torque is 0, when you make them at 0, that means the object will stay at the same, or stay at rest. They will not move. As we see in the example of seesaw. When we make them balanced torque, both of them now sitting at the same distance, having the same torque, so they will not move. They will not rotate. But once we have unbalanced torque, they start to rotate. As here we have this example. Example number 1, here we have a balanced torque. This case here, torque 1 is first the force 1 times the lever arm 1, or the distance 1. Torque 2 is the second force times the second of the distance of the lever arm. They are now here. They are balanced. They are balanced, so they stay at rest. They didn't move. Once they are not equal, they are unbalanced torque, like here. Torque number 1, they are F1 times L1. Torque number 2, they are F2 times L2. We will say that they are not unbalanced if the torque 2 here is greater than torque 1. If they are greater than it, so I will say that this is unbalanced torque. This is not important for us. Important for me now is the balanced torque. So the balanced torque, that's me. I want to make the torque at the right equals to the torque at the left. When they are equal, the object will not move. Here, how did we solve them? Let's have now these examples here. Two children are sitting on a seesaw, as shown. One of them has 300 Newton, and the second one was 500 Newton. Calculate the distance that the 500 Newton child should sit from the fulcrum or from the pivot point to balance the seesaw. So here now the distance from the first boy, 300, and for the second one, they are 500, and they have 500. They have 300 meters between the first boy up to the pivot point. I need now to find the distance from the second boy up to the pivot point in order to make them balanced. So what you have to do here, you have to say that the torque net is 0 since they are balanced. So the torque of the net torque 0. So the torque 1 must equal torque 2. Now let's find torque 1. Torque, as we said before, it is the force times the distance. So now what is the force here?
300 Newton.
And what is the distance? The distance is from the turning axis up to the pivot point. It's 3. 3 equals T2, which is 500. The force times the distance. This distance here, I don't know it.
Teacher, isn't it also 3?
No, we don't know. Here they told you that from this point up to this point is 6. But the boy is changing his place in order to make them balanced.
Okay.
So then here, 300 times 3, which is 900, equals 500x. So x will be 9/5. So that's mean the boy should set a distance from 1.8 from the pivot point in order to get balanced with the second boy. Is it clear?
Teacher, the last thing that you said, I don't understand, like how like here, like how the balance will be.
That's mean this boy here, let's color them. Okay, the purple boy will sit with a distance of 1.8 meter from the pivot point in order to get balanced with the second boy, the red boy, that's sitting 3 meters from the pivot point.
Like they will be balanced. So if they will be balanced, the meter here, like the distance here will be 1.8.
Yes, exactly. And when they are here, when they are at this point, let's draw them here now. Just a minute. The first case, they are sitting here. One is here, and the second one is here, and they are sitting with 3 meters from the pivot point. But as you see now, who is heavier? The orange boy. This is the orange boy, and this is the blue boy. Now, who's heavier?
The
was
400
the
Newton because
the second one. Who's the blue one? This is the heavier one. So since he is heavier, how will happen? Well, what will happen with the
he will
seesaw?
go up the
It will
orange
go
one.
down. The seesaw will go like this. Let's make them icon line. So since he is heavier, the seesaw will go like this. I want them now to get balanced. To get balanced, we found the torques of balanced torque. When we found the balanced torque, I go to the second, or I go to the blue boy. I tell them, please, I want you now to set 1.8 meter far from the pivot point. So they said that, okay, that's mean here. So now, when the boy come, I make like a story, by the way. When the boy is coming, he's sitting here now. When he is sitting here, they make the seesaw balanced. They change his place in order to set 1.8 meter from the pivot point. By now, when they change the distance, we make them have the same torque.
Yes, okay, teacher.
Are you sure it's clear now?
Yeah, thank you, teacher.
Yeah. The others, miss, is it clear with you?
Yes, teacher.
Yes, teacher.
No. Here. Suppose the meter stick is supported at the center and 220 Newton block is hung at 80 centimeter mark. So here now you have a meter stick starting from 0 up to 100 centimeter, or I mean like the length of the meter stick here, since it's named meter stick, so it's 1 meter. So the length now from this point here to here is 100 meters. At 80 centimeter, there's a 20 Newton block. And another block of unknown weight. Just balance the system when it is hung at 10 centimeters. So when it is at 10 centimeter here, there's a unknown weight. They are sitting now in a balanced torque. How can we find the weight of the second block? Since they are sitting in balanced torque. What we have to do here, we have to go to use the balanced torque. The balanced torque, that's mean the torque net is 0. That's mean torque at 1 is equal to torque at 2. Yeah, what is the torque at the first case here in number 1? It is the force
Force times distance.
times. What is the distance now? Now we have to find the distance. So where is the, yeah, wait, now this is the pivot point. The distance is the lever arm is the distance from the turning axis up to the pivot point. So here from the meter stick, it is 50. So 50 minus 10 will be
30.
40.
40, I mean.
First, yeah. So this is here will be 40 centimeter. But be careful, it must be in meters. So 0.4. Now the second case. His weight is 20. Now where is he sitting? Oh, where's the block? Now here is the pivot point at 0.50. So what is the distance will be? 80
minus
50, which is 30 centimeters.
30.
Which is 0.3. Why I changed them? Because the torque must be in Newton per meter. Then we need to find the force. So 20 times 0.3, which is 6, equals force times 0.4. So 6 over 0.4 will be 15. So the second weight here will be 15 Newton.
Teacher,
Yes.
teacher, can you repeat from where did you get the 0.3?
Okay. They told me from the question that the block is sitting at 80 centimeter and the unknown block is sitting at 10 centimeter or hanging at 10 centimeter. I need now to find the distance from where the block is hanging up to the pivot point. Then I need now to find the distance from this point up to the pivot point. Okay, this is the mean of D. Now he is sitting or this hanging at 80 and the pivot point at 50. How can I know at 50? If here is 40 and here is 60, so that between them will be 50. Is it right?
Yes.
Right. Now he is hanging at 8 centimeter. I want to find the lever arm, the distance of the lever arm. The distance of the lever arm means the distance from the turning axis, from the hanging point up to the pivot point. So if here is 80 and here is 50, subtract them. 80 minus 50 will be 30 centimeter. But since I need to write the torque, I will use the unit for the torque is a Newton per meter. So I need to rewrite it in meter. So that's why I write it as 0.3 meter.
Okay, thank you.
Got it? Yeah. Now, here.
Teacher,
Yes.
teacher, it does make sense because since the distance 0.4 is greater than 0.3, so the force will be less than the one that has the greater distance.
Sorry, but can you repeat?
So
No,
can
okay,
you go back? Teacher, I mean here it makes sense because since the distance is greater than the other one, which is 0.3, so the force will be less than the 20.
Oh yeah, exactly.
Make balance, yeah.
Now here, a boy and a girl are balanced on a massless seesaw. So here are balanced. So we are talking about balanced torque. The boy, so let's draw the seesaw first. The boy has a mass of 70 kilogram. And the girl has a mass of 60 kilogram. If the boy is set 2 meters from the pivot point, where must the girl sit on the other side? We need to find now this distance. So before of that, here, what did they give you? They give you the mass of the boy. But since we need to find the torque, we don't need the mass. We need the weight. And here.
So we'll make 70 times 100. I mean
so,
10.
Yeah. So the weight of the boy here, this is the boy. And this is the girl. So the boy here will be 700 because I multiply 7 times 10. And the girl will be 600 because I multiply 60 times 10. So I have now the weight. What did I need to find? I need to find where the girl must sit on the other side to get balanced with the boy. What we have to do? Torque net is 0.
Equals 0.
So torque 1 must equal torque 2, or torque of the boy must equal torque of the girl. Now torque of the boy, the force times his distance 2. And torque of the girl 600 times the distance, which is x. Then 700 times 2, 1,400, 600 x. So x will be 1,400 over 600 x. So the distance will be 7 over 3 meters. In decimals, they are sitting now on 2. The girl must sit at 2.3 meters in order to get balanced with the boy. Is it clear?
Yes, teacher.
That's it. Do you have any question? Do you have any question?
No, teacher, for me, everything is clear.
Okay.
It's for me too.
Teacher, do you know when is the physics exam and the math exam?
That will
Like it will